This week, 3 theories that have changed the way we view the world: relativity, the quantum theory, and the Big Bang. In Rome in the year 1633, the Inquisition condemned the physicist Galileo to house arrest for life. His crime? To have proclaimed that the Earth was round and moved around the sun. Despite his condemnation, Galileo's vision revolutionized our concept of the world. 4 centuries later, another young physicist would do it again. Who would have believed that one of the greatest scientific revolutions of all time would originate from a junior clerk in a patent office? And yet it is true. In 1905, when he was only 26, the young Albert Einstein was formulating a theory that would throw the scientific community into confusion: the theory of relativity. The concept itself was not Einstein's. It first came from the Italian physicist, astronomer, and mathematician Galileo, born in Pisa in 1564. Before Galileo, it was thought that for any given object, say a boat, there existed only one natural state: rest. Motion was perceived as a fundamentally different, unnatural state. False, said Galileo. Indeed, the latter had observed that if a passenger on a boat does not refer to any external landmark, he cannot tell whether his craft is moving or not. For example, suppose the passenger drops a ball. When the boat is at rest, the ball seems to fall to the floor in a direct line. When the boat moves at a constant speed, it stays the same. For the passenger, the ball always appears to fall vertically. For Galileo, the reason for this phenomenon was simple. The physical laws governing the motion of objects are the same whether we are moving or stationary. In short, motion and rest are not absolute, but relative states. When Einstein came onto the scene at the turn of the 20th century, all material objects seemed to satisfy that theory of relativity. Thus, even though the Earth rotates at a speed of 11 kilometers per second, the ground seems stationary. This explains how children can play with a ball without it landing miles away. Unfortunately, there is an exception to his theory: the movement of light. In Einstein's day, the assumption, well established, was that light waves always move at the same speed, regardless of the point from which they are observed. However, Einstein felt this contradicted the relativity principle. Let's board a train this time, moving at a speed of 100 kilometers per hour. And imagine a passenger at the rear of the train walking toward the front at a speed of 5 kilometers per hour. For a stationary observer located outside the train, the passenger will appear to be moving not at a speed of 5 kilometers per hour, but at 105 kilometers per hour. This confirms the relativity principle whereby the speed of the passenger is relative to the speed of the train. Unfortunately, that simple rule of addition no longer applies where light is concerned. This time, our passenger, located at the rear of the train, sends a pulse of light toward the front, using a flashlight, for instance. In relationship to the passenger, the flash of light will move at the normal speed of light, namely 300,000 kilometers per second. But for the stationary observer, the speed of the pulse of light should be added to the train's speed. However, this is not the case. Light always seems to travel at the same speed, regardless of who is observing it. To solve this strange contradiction, Einstein came up with what seemed an equally strange idea. He claimed that if the speed of light was constant, time, on the other hand, was elastic. In other words, time does not travel at the same speed for a stationary observer and a moving observer. The following experiment proves it. Standing in the middle of a car, our traveler simultaneously directs two beams of light, one toward the front of the railway car and the other towards the rear. When they reach the front and rear ends of the car, the pulses of light open a door at each end. For the passenger, the two doors open at the same time because the pulses of light reach both ends at the same time. But for the observer standing on the platform, the two doors do not open at the same time. Indeed, the rear end of the car seems to go and meet the flash of light, whereas the front end seems to run away from the light. The result? The beam reaches the rear door first, and the front one only later. The rear door will therefore open before the front door does. This type of experiment, which Einstein called a thought experiment, proves that time is not, as had previously been thought, absolute, but relative, and its motion depended on the motion of the person measuring it. But relativity effects are only observed at speeds close to the speed of light. For example, Einstein predicted that on a spaceship traveling at such speeds, time would go by much more slowly than on Earth. This is the twins paradox. Imagine twins. If one twin is traveling in space at a speed close to the speed of light, while the other twin remains on Earth, the latter will age much more rapidly. But Einstein also asserted that nothing could travel faster than the speed of light. No object can, in fact, ever reach the speed of light, because by then its mass would have become infinite, and it would have taken an infinite amount of energy to get it there. Whether science fiction fans like it or not, the speed limit is irrevocably set at the speed of light. The theory of relativity doesn't have an answer for everything. It is ineffective when it comes to explaining what occurs on a very small scale, inside atoms, for example. To find this out, we have to refer to the quantum theory. There are two main types of phenomena in our world, light and matter. But what are they really? It was to try and answer that question that at the turn of the 20th century, physicists began constructing the quantum theory. Up until then, physicists divided natural phenomena into two categories, waves and particles. A particle, a rock for instance, is an object that is confined in space. Its position is easily determined. However, the wave created when the rock is thrown into the water spreads out in all directions. It is a continuous occurrence that cannot be confined. Early in this century, it was thought that light was made of waves. Indeed, every color in the light spectrum was seen to match a different wavelength. The red waves being, for instance, about twice as long as the blue waves. Conversely, atoms, small bundles of matter, were seen as particles, themselves made up of smaller particles, namely a nucleus around which one or several electrons orbited. However, a simple observation challenged these models. If, for example, a block of iron is heated, according to classical physics, it should emit the entire spectrum of light wavelengths. But that is not at all what is observed. From its initial black color, the block first turns red, then white. Finally, it turns ultraviolet. The block of iron seems to jump from one wavelength to the other. This challenged classical physics. To solve the puzzle, physicists were forced to admit that light is produced in the form of minute particles of energy, photons. Each photon has a distinct color. The successive color changes in the iron block are due to the fact that at a given temperature, the block's atoms emit mostly photons of the same color, corresponding to that temperature. But physicists also realized that the atoms themselves were not as they had imagined. Contrary to what they believed, the electrons do not have a fixed path around the nucleus of atoms. For example, on the surface of the sun, atoms collide violently. These collisions send the atomic electrons on to a higher orbit. They then fall back to their initial orbit, releasing a photon of light. It's a little as if the electron went up a stair and then back down again, each time releasing a specific amount of energy. A same electron can orbit around the nucleus following more than one path. Taking their research a step further, physicists observed that the number of paths an electron can take is in fact infinite. In other words, it is impossible to know the position of an electron at any given moment. One can only assess its probability of existence at a specific location. That probability of existence may be represented by a fuzzy wavelength floating round the nucleus of the atom. Through these findings, light, thought to be a wave, also became a flux of particles, and the electron, thought to be a particle, also seemed to possess wave-like properties. This new concept of light and matter revolutionized scientific thinking. Until then, it was thought that in nature, a same cause would always produce the same effects. For example, by knowing the position of the ball he is aiming at and exerting a given force on his cue, an experienced billiard player would probably sink his ball into the pocket. But if the billiard balls were to display quantum behavior, things would be altogether different. When motionless, the balls would be quite visible. But once in motion, their path would be such a fuzzy cloud that it would be impossible to locate them. Even worse, the balls might go in a direction diametrically opposed to the path intended, going, for instance, 180 degrees off the chosen direction. Even an ace player would have little chance of hitting the mark. Fortunately for billiard players, the quantum theory applies generally to the world of the infinitesimally small, and with great success. For example, thanks to the quantum theory, a microscope has been developed that can see atoms, something once thought impossible. The principle of the tunneling microscope is simple. It is a tiny probe with a single atom at its tip that images surfaces. The tip scans the surface of the object being studied so closely that the electronic cloud of the atomic probe and that of the object's atoms overlap. An electric current then goes through the space in between. The smaller the distance between the tip of the probe and the object, the greater the current's intensity. By scanning the surface of an object, we can provide an extremely accurate map of that surface. In some cases, the map will reveal what no microscope has ever been able to show: the material's individual atoms. While he himself was one of its founders, Einstein found himself in disagreement with the quantum theory. God, he said, does not play dice. These fascinating images, however, would seem to prove that the game of dice is indisputably one of God's favorites.
No scientific theory is considered immutable today. However, to explain the age-old enigma of the origins of the universe, a recent theory, the Big Bang, is increasingly receiving the approval of the scientific community.
Where do we come from? A question humankind has always asked itself. Parents will tell their children they came from the fusion of two small cells, the ovum and the sperm. Biologists, however, will retrace evolution back to the very first living being, the simple bacterium. But physicists have gone even further back into the past. They have, in fact, formulated a plausible and coherent theory of the origin of the universe. According to that theory, which is called the Big Bang, the universe did not always exist, at least not as we know it today. It would have come into being about 15 billion years ago in a unique explosion. Gigantic in intensity, but minute in size, the explosion would have created the time, space, matter, and energy that make up our world. In order to reconstruct that amazing scenario of the birth of the universe, scientists of all disciplines joined forces. The astronomers found the first piece of the puzzle. They had known for several decades that most of the stars, such as our sun, were grouped in mammoth clumps called galaxies. Now, galaxies are not fixed in the sky. By analyzing the colors of their radiation, the researchers were able to observe that the galaxies all seem to be moving away from ours. And the farther away they were, the faster they seemed to be moving away. This discovery led them to conclude that the universe was expanding. Indeed, imagine the universe as a balloon being inflated, and the galaxies as dots painted on its surface. We will observe that the dots move away from each other as the balloon is blown up. If we were on one of those dots, it would seem the other dots were moving away from us, with those farthest moving the fastest. That is precisely what is happening with our universe. Why is our universe expanding? To understand that, we have to imagine it running backward. We would see the galaxies getting closer and eventually come together in a single point, about 15 billion years ago. This led the scientists to suppose that the universe had a beginning and originated from a tiny point and with a strange explosion. However, in order to be sure, additional proof was needed. One of the most convincing was discovered in 1964 by two electrical engineers with Bell Telephone Laboratories. Penzias and Wilson had used a special low-noise radio antenna to try and identify the static that was interfering with satellite communications. By sheer accident, they happened to detect a sort of cosmic background noise that seemed to be coming in from all directions in space. The radiation was of the same nature as the microwaves of a kitchen oven, but it was much colder. According to Penzias and Wilson, the radiation had to be a sort of echo of the primeval explosion. If the scientists were able to reconstruct the conditions at the birth of the world, it was in part thanks to particle accelerators. These tremendous devices bombard matter with energy, allowing the scientists to study how matter stands up to very high temperatures and pressures. Such experiments, together with the calculations of the physicists, allow us to assume that in the beginning, the universe was infinitely small, infinitely dense, and infinitely hot. This bubbling soup contained the elementary particles that would make up matter, as well as those that would form light. But the temperature began to drop, and events followed each other in amazingly rapid succession. In a mere fraction of a second, particles of matter called quarks combined to form protons and neutrons. 2 long minutes later, the protons and neutrons in turn combined to form atoms. However, because it was extremely dense, the cosmic group held light captive. The universe was therefore an opaque mass. However, 100,000 years after its birth, both the temperature and density of the universe had considerably decreased. Freed from matter's grasp, the light particles began to travel through space. The universe then became transparent. That gigantic flash of lightning, today cooled, is the origin of the radiation detected by Penzias and Wilson. Recently, a NASA satellite provided scientists with another piece of the puzzle. It involves very slight variations in the intensity of the cosmic background noise. For astrophysicists, this finding seems to indicate that the primeval universe was not uniform, but presented irregularities that resembled lumps in a soup. Through material condensation owing to gravity, these cosmic lumps produced the galaxies. This was the starting point that would lead to the formation of the stars, the planets, and much later, the emergence of intelligent life forms capable of wondering where they came from.
Perhaps the Big Bang does explain the origin of our universe, but what about its fate? Some claim that the universe will eventually contract to become infinitely small again. There would then be another Big Bang, which would create another brand new universe.